then let's return to our topic last time when we were just beginning to look at the bipolar junction transistor. So let me go ahead and re-sketch what we had last time. Okay, so last time we were looking at the structure of the NPN transistor, where we have an N-type emitter, a P-type base, and an N-type collector, so an NPN transistor. And as we mentioned before, since we are merging an N and P region together, we're going to have a depletion region that forms between the base and the collector and the base and the emitter, just as we would with a PN diode. So in this case, I'm going to go ahead and add a couple of voltage sources. VBE and VCB. So this connected between the base and the emitter. This connected between the collector and the base. So notice the subscripts. And in both these cases, I'm going to have these voltages as positive voltages. So if we look at this, I'm going to take VBE and increase it to the point where I forward bias this PN junction between the base and the emitter, which means that VBE is going to be approximately 0.7 volts. So the emitter base junction is forward biased. On the other hand, for VCB, I'm making the N-type region more positive than the P-type region. The collector is more positive than the base. So in this case, the collector base junction is reverse biased. So it's going to be some positive voltage, but it's not going to be limited by a junction turn on or anything like that. So this particular region of operation is called forward active operation, or the forward active region. And I want to emphasize once again, and we talked about this before, the doping of the emitter is typically much higher than the doping of the base, which in turn is typically much higher than the doping of the collector. So we go from highly doped to moderately doped to lightly doped between those three regions. And we notice because of this, we note, unlike a MOSFET where the source and the drain can be interchanged because it's symmetrical, this is not a symmetrical device. All right, so how does this thing work? Well, this was, of course, the trick that it took the guys at Bell Labs to figure out. The field effect transistor had a very simple mental model. You form a channel and current flows through the channel, which is why everybody tried to pursue it for so long. This was a less than obvious model, and the guys at Bell Labs understood the p-n junction very well, and it took them a while before they realized, as later on as the inventors of the transistor said, they stumbled across a solution that was kind of underneath, right beneath their, basically a solution that was right in front of them all along. And it took them a while to suddenly click and make it understand. But in order to do it, they had to kind of go to a totally different way to how this device works. So let's think about how this is going to work. First of all, let's focus on this forward biased junction between the base and the emitter. So there's going to be current flow. It's a forward biased junction. And in this case, electrons are going to flow out of the negative end into the emitter. Holes are going to flow, and once again, we are thinking of holes as if they were positively charged particles. That's just the way we would try to create that model, that mental model. So holes are going to flow in this side, electrons are going to flow into this side. But you notice, there is an asymmetry in the doping. There's a lot higher doping in the emitter than there is in the base. And so what's going to happen is, as current starts to flow through this base emitter junction, and as the depletion region gets narrower and it's easier for carriers to diffuse across that depletion region, we have a lot more electrons going from the emitter into the base than we have holes diffusing from the base into the emitter. And that asymmetry is because of the much higher doping of the emitter. All right? So, electrons are diffusing emitter to base, holes from base to emitter. What happens here? Well, once the holes get over to the n-type region, they're going to recombine with the electrons that are being injected into the emitter. And as electrons travel into the base, they're going to recombine with the holes flowing into the base. So if the holes and the electrons recombine as they enter the emitter and the base respectively. So they enter, they are canceled by the electrons and the holes traveling in. So it's the same kind of thing we saw with a forward bias junction. But because of the asymmetry in the number of carriers diffusing across that junction, what we find is we have a lot of excess electrons that do not immediately get recombined, because there's nothing for them to combine with immediately. We don't have enough holes to satisfy all of the electrons coming across. And so you've got free electrons basically in this base region, and they haven't yet combined with a hole. So I've got a whole bunch of extra excess electrons in that base. But think about this. I've got electrons in a p-type diffusion. What is an electron in a p-type diffusion? It's a minority carrier. Electrons in a p-type base become minority carriers. Okay, majority carriers travel across a forward bias junction. We saw that before when we looked at the PN diode. What can travel across a reverse bias junction? Minority carriers. So all of these electrons that are here, that are acting basically as minority carriers, they haven't had time to recombine with any holes in the base. Well, what do you know? They can drift right across this reverse bias junction, attracted by these positive charges, and head into the collector region. Those excess electrons travel across that reverse biased collector base junction. At that point, the collector base voltage source supplies holes. All the excess electrons drift across, and so some are captured and recombined. Some are, but the majority of them actually make it across that reverse bias junction. And at that point, we have holes flowing in from this side, and then they recombine. This is the process. It turns out that the number of holes you need to inject into the base to cause this process to happen is very small relative to the number of electrons that make it from the collector through the from the emitter through the base and into the collector. And so what we have here is, once again, thinking about current. Positive base current is in the direction of holes. There's your base current, I sub B. There's your collector current. Here's your emitter current. Emitter current is opposite the direction of electrons. And that is, in effect, how the emitter base, how the bipolar junction transistor works. So once again, once the guys at Bell Labs understood the process, and it was really, when you think about it, it was really Bill Shockley who sat down and thought this out. Because Bardeen and Brattain came up with a structure that worked, but really wasn't practical. He actually sat down and thought about how to build this layered type of structure and make this work once he understood the mechanism. And so basically a large part of the design of the modern transistor really comes from his original thinking. So here is our transistor. The emitter emits electrons. The collector collects most of those electrons. So that's where emitter and collector come from. And the base is, in effect, the controlling terminal. All right? So once you understand how a PN junction works, this is pretty straightforward. Yes?
So does that mean that the voltage B is 0.7 and then the voltage CB is just less than?
Well, VCB can be any positive value because you're just reverse biasing the diode, the PN junction. So it doesn't have to, it's not going to be limited to any particular value. I mean, obviously, if you make it a large enough value, you can make the collector-base junction break down. But that's not something you normally want to do. Okay, so our result. A small base current, I sub B, results in a much larger collector current, I sub C. And I also want to point out, this forward active region is the desired region of operation for amplifier design. So just as saturation is desirable for MOSFETs, forward active is the desirable region for this type of structure. So, as we're going to see, most of the practical circuits we're going to build are going to be in forward active operation. Now, for reasons we're going to talk about later on, bipolar junction transistors make perfectly good amplifiers. They don't really make good switches. You can take a MOSFET transistor and push it into the triode region and make it behave like a switch with VDS goes to 0, and it works perfectly well that way. In fact, that's why all of our digital circuits nowadays, all of our digital designs are based almost entirely on MOSFET transistors. Bipolar transistors don't work so well. In fact, you can actually have failure mechanisms that occur. So we'll talk about that later on. But this is why bipolar is really not found in digital logic. You can make digital circuits with them, but they don't work nearly as well or as efficiently as you can do with circuits built with MOSFETs. So that's really one of the reasons I said before, that when you look at MOSFETs, they are primarily what people use nowadays in circuit design. There are far, far more MOSFETs out there than BJTs because we're using them in all of our digital designs. Okay? So, fairly simple mental picture. Once again, not going into any details. And of course, many of my colleagues would be completely horrified at my, arm-waving lack of detail. But once again, I just want you guys to have the mental picture. But if you understand how the p-n junction works, then this kind of makes sense. Everything seems straightforward. Okay, so now we're going to jump right into the equations. Given this structure, what are the design equations we're going to use? First of all, IC is a function of the base emitter voltage. Does that equation look familiar to everybody? It should. The collector current is equal to I sub S times e to the VBE over VT. That's the diode equation, the p-n diode equation for forward bias. And since the base emitter junction is forward biased, we're going to use basically a form of the same equation. Except in this case, IC is equal to IS, e to the VBE over VT. VT, of course, is once again 25 millivolts. It's our thermal voltage. That is not different. I sub S is our saturation or scale current. So this equation we've seen before, But the interesting part, as you guys are going to see later on, is we're actually going to really use this equation very little. In fact, almost not at all. Turns out there are more useful equations we can use. Looking at this, let's look at this diagram. And let's think about KCL. So IB and IC, what goes into the transistor must be what comes out. IB and IC go in, IE comes out. So by KCL, IB plus IC is equal to IE. And we note since IC is typically much, much greater than IB, what we find is IC will be approximately equal to IE, typically within 1% or less of the two values. So like I said before, only a tiny amount of base current is required to make that current flow through that circuit. Well, we define a parameter with this. Beta is our current gain. As we said, IC is much, much greater than IB. There's a mathematical relationship between the two. IC is equal to beta times IB. And typical values of beta for commercial transistors tend to be in the range from 50 to 300. You guys are going to be using the 2N2222 in your labs a lot this semester, and I think that's normally got a beta of about 150. So that's kind of pretty typical. All right. Now, something I want to emphasize to you guys, beta is not a constant. Anybody in semiconductor physics will tell you that. Beta is going to be a function of your collector current, as well as a lot of other factors depending upon the values of the currents in your device. But as far as we're concerned, we are for the most part just going to treat beta as a constant, just to make it easy. But in more advanced courses, you'll find that beta tends to vary at both very low collector currents and very high collector currents. It's going to reduce. All right? Well, given this, I can take this and plug this into that. And if I do that, then I'll get the following. IB plus beta IB is equal to IE, and therefore IE is equal to beta plus 1 times IB. Or it's equal to beta plus 1 over beta times IC. So IE is slightly larger than IC, but if beta is big, if beta is large, then this tends toward unity. All right? And of course, I can take this equation here and I can plug it over into here. I can also write an equation for IE in terms of the scale current and VBE, just adding in that beta plus 1 over beta factor. But again, as I said, we don't normally use these exponential forms, and you guys will see later on why that is true. All right? So, given these equations, a couple other terms I want to define. We also define alpha, which is nothing more than beta over beta plus 1. And typically this is going to be 0.99 or higher. Because beta is going to normally be large. Or I can say that beta is equal to alpha over 1 minus alpha. And so again, you will see alpha and beta both used in these transistor equations. And IC is equal to alpha times IE. So notice all these equivalent equations I get just by using a little bit of algebra. And again, you're going to have these equations in front of you during the exam. Okay, there's no need to memorize this, but I just want you to be aware of them, and you want to definitely be using them and get comfortable with them. Yeah?
I have a question about the transistor.
Yes, uh-huh.
Is IC caused by VCB or by the current that is?
Well, it's a function. IC is a function of VCB being a positive voltage, so of course it supplies holes. Okay, it supplies positive current. But the current's able to flow across the reverse bias junction because we have lots of excess carriers, which are minority carriers in the base. But yes, the current's coming out of VCB, okay? So what's happening here is the current's flowing out of this source and then back into this source. All right, notice there's a connection between here. So KCL is going to apply here, and it's also going to apply for the transistor. Yeah, without well, you're saying without this?
Without the base, without the current that's going through the base, without IB. You can't have IC, right?
Yes. We've got to have base current. And the reason is the base current flowing is what forward biases this junction and causes the depletion region to narrow so that carriers can diffuse across it. So that's what forward bias does. You've got to forward bias the junction. And then you're going to have holes flowing into the P region because you're connecting that source to forward bias it. So this is nothing more. If you just look at this right here and just ignore the collector region, that's a PN diode. We already analyzed that PN diode. That is no different than what we talked about a couple of weeks ago. The only difference here is now we're adding on that collector region. We got a reversed bias region, and the excess electrons, which turn into minority carriers in the base, can be captured by that collector, and they can sweep across that reverse bias junction. Well, the collector is going to capture these electrons in this N region because we're able to supply holes from this source here in order to cancel those out. So the holes in the electrons are going to annihilate each other. Yes. So keep in mind what happens in a p-n junction. As these p-type holes drift across, they're annihilated by the electrons. They recombine. As the electrons drift into the base, they're annihilated by the holes, which is what we saw before for the p-n junction, all right, for the simple diode. But in this case, because so many more electrons cross this depletion region than holes, they don't recombine immediately. And so while they're drifting in that base, they can then drift over to this region, be captured by this reverse bias junction, and then be attracted by those positive by the positive charge in this depletion region, then be swept into here, and then they're annihilated by the holes flowing through here. So if you take a reverse bias p-n junction, if I do this, I have a reverse bias junction. And once again, ignoring this, a reverse bias junction, the only current that flows across a reverse bias junction is going to be the minority carriers. So normally, just by itself, if this were reverse bias, there'd be almost no current flowing across that junction. But in this case, we are artificially supplying that P region with a ton of excess carriers, a ton of excess minority carriers. They're coming from the emitter. Then once they're in the base, as far as this reverse bias junction is concerned, oh, we've got all these excess minority carriers here. They can travel right across a reverse bias junction, and that's exactly what they do. So that's what's going on. And once they realized how this worked, then they could see how they could get current gain out of the structure. Yeah? Here? Oh, up here? You mean this? Because VBE is the forward bias of the diode. Okay, so VBE, VD is what we had in the diode equation. That was the forward bias for the diode. VBE is the forward bias junction. No, it's actually IC, okay? Now, could you scale it against that? Sure, you can scale it by using that beta over beta plus 1. But if you're asking me for a reason, a semiconductor reason derivation for why this equation versus the other, first of all, I'm the wrong person to ask. And secondly, this is the wrong class. So I'm just going to once again say, this is the equation. If you want to learn where that equation comes from, in fact, if you want to learn how to derive that equation from first principles, there are much better professors to take this stuff from them than me. Okay? I'm a circuit designer. I'm not a semiconductor physicist. So I will, right off the bat, plead ignorance as to why this particular equation has IC instead of IE. Beyond the fact to say that as long as I define IS as beta plus 1 over beta times IS, I can write it that way. So it all depends upon what you define your scale current as, whether you want to add this multiplier or not add that multiplier. That's really what it comes down to. All right? Okay, so this is our forward active region of operation. Emitter-based junction is forward biased, collector-based junction is reverse biased. But there are other regions of operation. Actually, let me go down here. What if VBE is less than or equal to 0? What if VBE is negative? In this case, the emitter-based junction is reverse biased. So in this case, if the emitter-base junction is reverse biased, there are no carriers flowing between the emitter and the base. And in that case, there's no excess carriers to go over to the collector. So in this case, if the EBJ is reverse biased and the collector-base junction are reverse biased, then the transistor is in cutoff. And in this case, both IE and IC are approximately equal to 0. Yeah, there can be a very, very tiny reverse bias current can flow between that reverse bias emitter base junction, but effectively the transistor's off. So just as when you have a reverse bias diode, you can have a tiny current flow. But in this case, they're both effectively off, effectively equal to 0. All right? What if they are both forward biased? What if I make VCB negative and I forward bias the collector base junction? So in other words, what if VCB is less than 0? Then that is another region of operation. In that case, we say the transistor is saturated. Okay, words and definitions. Saturation, we've seen that word used twice before, had totally different meanings. Saturation in an amplifier, as we talked about before, is bad when an op-amp saturates. Saturation for a MOSFET is good. What about saturation for a BJT? Bad or good? Anybody want to guess? Bad. Saturation is bad. This is very undesirable. Extremely undesirable. And we're going to see later on why that is true. Just as with an amplifier, an op-amp that is saturated, a BJT that is saturated does not function as an amplifying device. So, definitions. Op-amp saturation is not equal to MOSFET saturation. And that is not the same as BJT saturation. Same word, completely different meanings, completely different mechanisms. This is bad, this is good, this is bad. Sorry for the confusion, but we're going to use those terms because, once again, those are the terms that everybody uses. It's the convention. You just have to understand and remember they mean totally different things. Okay? Questions? Questions so far? Okay. Now, incidentally, there is a fourth region of operation that we can have, and I'll talk about in a minute. There's a region of operation I can get if I swap the collector and the emitter. In a MOSFET, swapping the drain and the source is no big deal if it's a symmetrical device, because the drain becomes the source and the source becomes the drain. But in a BJT, because of the doping levels, that's not true anymore. And so, as we're going to see in just a minute, there is also a fourth region of operation, a reverse active region, which doesn't work very well and is almost never used, but it does exist. But basically about the only way you can have reverse active is if you put the transistor in the circuit backwards. Then you'll know very quickly you did something wrong because the circuit simply won't work. All right? So just to add a couple other things to this. There is a large signal model you can use for this, for the BJT. There's a large signal model for forward active operation. And incidentally, typically people just drop the forward. When they're talking about forward active in BJTs, they'll just say active. Just drops the word, but people know what you're talking about. So for active operation, here's a large signal model. So here's our large signal model. In this case, we literally just model the base emitter junction as a diode. That and nothing more. Then we have a dependent current source, which simply is dependent on the base current, IB. And that's equal to beta times IB, or it's equal to IS times e to the VBE over VT. And then we have the emitter current flow at the bottom. So in forward bias, this is basically what the thing's behaving like. And notice this dependent current source behavior. And as we're going to see later on, the fact that these transistors behave like current sources or dependent current sources is what makes them useful as amplifier circuits. Okay? Now, I also mentioned before that the structure of the BJT I drew for you guys isn't really what they look like. I mean, that sandwich the way I drew it. As I mentioned before, and I just want to reiterate this, is that an actual transistor structure really looks more like this. A vertical NPN transistor structure in an integrated circuit will look like this. So here's our P substrate, and then we're going to have a very highly doped emitter. And then a moderately doped base, and notice right underneath the emitter it'll be very thin. That base region will be thin. And that's deliberate. We want that base region to be thin because we want to make it very easy for the carriers, the excess electrons, to drift through that base and be captured by the collector before they can recombine. And so the thinner the better. And then we'll have our collector. So an N++, a P+, and then an N. So the emitter is more highly biased than the base, which in turn is more highly biased, probably more highly doped. Emitter is more highly doped than the base, which in turn is more highly doped than the collector. We also note that the collector-base junction area is going to be larger than the emitter-base junction area. All right? So, as we mentioned before, because of the asymmetry of these structures, the emitter and the collector can't really be swapped. If we swap the emitter and the collector, the transistor will operate in the reverse active. So if I've got a transistor operating in forward active and I just swap the base and the collector, it'll keep on working. But the problem is the collector makes a terrible emitter and the emitter makes a terrible collector. What will happen is this. The beta will be very low. So you may go from a beta of a couple of hundred in forward active, and you flip it around and you may have a beta less than 1. So reverse active works, but not well. You don't get the current amplification you want out of it. No, it's not the same as saturation. So in reverse active, I'm assuming that now the base collector is forward biased and the base emitter is reverse biased. So in this case, I'm just swapping the reverse and the forward and reverse bias between the two regions. In order to be saturated, they've both got to be forward biased. All right? Yes?
What happens?
Well, in terms of how the circuit behaves in saturation, we're going to get to that. Don't worry. So no. We're actually going to see how you can figure out if the transistor is saturated. Because although saturation is not an intentional region of operation you want to have happen, it's very easy to make it happen by accident if you don't bias the circuit correctly. So same thing with MOSFETs. You don't want to normally be in the triode region of operation. So you have to be careful. You have to understand how to discern between the regions. And we'll see how to do that in a little while. Okay? So this is generally not used, reverse active. I mean, I'm not going to talk about any circuit applications unless you deliberately try to do it or accidentally do it by swapping the collector and the emitter. It's never going to happen. So we're not going to really spend any time on it. But interestingly enough, there actually was a whole class of circuits back in the 70s, late 60s, 70s, TTL logic, transistor logic, where for reasons I have never bothered to sit down and try to figure out, the designers actually deliberately took advantage of reverse bias transistors to build those logic circuits. So it's a little bit of interesting circuit history if you want to look at that. But since then, there have been very few applications where people have done it. All right? Questions? All right. Now, I just want to point something out. This large signal model, as you guys are going to see, we're not really going to use it very much. Let's think about this for a moment. That exponential form. When we were doing diode circuits, diode problems, did we normally use the exponential form to calculate the diode current for most of the problems? What assumption did we make for diodes whenever we were solving circuits with diodes in them that were forward biased? What assumption did we use to make our math easy? Constant voltage drop. Yeah. Turns out we're going to use the constant voltage drop assumption with BJTs as well. So that's what I was saying earlier to you guys. We don't normally use that exponential form of the equation. For the same reason we don't normally use it for diodes. For diode circuits, we assume the constant voltage drop, and that is good for hand calculations. Same thing with BJTs. We're going to see that the constant voltage drop assumption is going to be the thing we use in most of our calculations. So let's look at some BJT symbols here. How do we draw the BJT? Now, just as with MOSFETs, BJTs can come in two flavors. I can have NPN, which is what I just drew, but I can also do PNP and make the emitter and the collector P-type regions. So in this case, here's my collector, here's my emitter, Here's my base. For the PNP, the emitter, we normally draw on the top, the collector in the bottom. And why do we do that? Well, we do it for the same reason that we do for PFETs. Because the emitter is typically more positive than the collector in a PFET, and current's going to flow this direction. So the same thing for the PNP. Positive current's going to flow from emitter to collector. For the NPN, positive current flows from collector to emitter. So some parallel between the MOSFET and the BJT in terms of how we draw them. Once again, I think you have to be careful because I think LT Spice, when you pull out a generic PNP model in LT Spice and drop it into your circuit, I think it always puts the emitters on the bottom. So you got to be careful about that. You'll quickly find that your circuit isn't working because you got to flip the transistor upside down. Okay? Let's define a few terms here. Let's see. Let me redraw this here a little further away. So VCB, VBE, so this is the voltage between the collector and the base, between the base and the emitter. Collector current flows in, emitter current flows out, positive base current flows in, which we've already seen. For the PNP, we have VEB, voltage between the emitter and the base, and VCB, voltage between the collector and the base. Probably between the base and the collector, excuse me. And in this case, IE flows into the emitter, IC flows out, and IB flows out of the base. So notice the difference in the directions for emitter, base, and collector current. We're flipping the directions, going from NPN to PNP. All right, now also looking at this, just to do a few definitions here. Let's define two voltages, VCE and VEC, the voltages between the emitter collector and between the collector and the emitter. And if you look at this, you can write a little KCL equation here. So, VCB plus VBE, adding those two voltages together, that's equal to VC minus VB plus VB minus VE. The base voltages cancel out, and this is equal to VCE. So just KVL, you can just see how the subscripts work. And so by definition, these two voltages must be equal to VCE. Now, for the PNP transistor, we note that VEB is going to be 0.7 volts. So just once again, we are forward biasing that emitter-base junction, or VBE is equal to minus 0.7. So again, the book likes to use positive values. So instead of saying VBE is minus 0.7 volts, it prefers to use VEB, positive voltages. In this case, VCB is less than 0, but for the PNP, VBC is greater than 0. So this means our emitter-base junction is forward biased. This means our collector base junction is reverse biased for the PNP. So we're just flipping those around. Okay. And for the PNP transistor as well, just for completeness sake here, hold on. IC will be equal to IS times E to the VBE over V sub T for a PNP transistor. So current directions are flipped, voltage polarities are flipped as well. Although the book will typically flip around the subscripts just so they can make things positive again. Okay? Now that we've kind of covered all these basics and we got our definitions here, let's talk a little bit more about regions of operation. As we've seen here, there are actually 4 possible regions of operation. Let's take our NPN transistor, and I'm going to do a little 4-quadrant plot. Okay. So what we talked about a minute ago, let's think about where we're going to map those 4 regions. So here, I've got VBE is positive, VBC is negative. In this quadrant, I'm in the active region of operation. Now, if I make them both forward biased, then I wind up in saturation. If I make them both reverse biased, then I'm in cutoff. And if I flip them so that VBE is reverse biased and VBC gives us a forward bias across the collector base, then I am in reverse active. So this kind of like graphically shows you what the 4 regions are. This is desirable. This is fine if you just want to turn the transistor off. This is undesirable, and this is almost unheard of. You know, you've really kind of got to go out of your way, as I said before, or by accident make something reverse bias, or reverse active, rather. Okay, so here are our 4 regions. The question is, what region is the transistor operating in? Let me draw a circuit. So here's our first circuit, NPN transistor, and I want to analyze the circuit and determine the currents in this circuit, IB, IC, and IE. And here is VBE, and here is VBC, the voltages across those 2 junctions. So I give you this transistor, and there are 4 regions of operation. which of these regions is this transistor operating in? Which of the 4? Can you look at that and by inspection tell me which region it's operating in? I got news for you, I can't either. What do I have to do? And we've already seen this before. Given a device and you don't know the region of operation, what do you need to do? Make an assumption, do the calculations, check the boundary conditions, and make sure your assumption was correct. Exactly the same thing we saw before. Okay? So, our procedure for all the transistor circuits we're going to be doing from now on is exactly the procedure we saw with diodes and MOSFETs. Make an assumption about the operating region, solve for the currents and voltages based on that assumption, and then check your assumption. What is generally going to be a good place to start, assuming the transistor is on? What region would you start with? Active. And why is active? Because that's normally what we want to make the transistor operate in, is in the active region. So that's normally a good place to start, but as we're going to find out, it's not always going to be in the active region. And one of the things you want to be able to do is discern when it is actually operating, for example, in saturation, or if it's even cut off. So next time we'll return to this, and then, just as we did with MOSFETs, we're going to work some DC problems. Okay? So see you guys on Thursday.